Hey, welcome to Chapter 8. Now, Chapter 8 is all about solutions. And Section 1 is specifically about the types of mixtures. We're going to start with mixtures. So, here we go. Solutions. Our definition of solution is a mixture of two or more substances. And this can be, take a bowl and put a bunch of salt and pepper in it and stir it around. That's a mixture. Remember, mixtures are not chemically combined. So they really are two separate things. Now that can be hard to tell when you've dissolved something in it, because salt and water is also a mixture. You're not chemically combining anything, but they do separate. The ions separate, but they haven't chemically combined with anything else yet. So mixtures, they can get a little tricky. First, we're going to start with homogeneous mixture. Vocabulary alert. An homogeneous mixture is where the solution is the same throughout the mixture. You can't identify the two parts separately anymore. And salt and water together are the perfect example of this. You can't see here's where there's more salt and here's where there's less. That it seems to be the same throughout. As opposed to, oh, here we go, example, salt water. Sand water. If you poured sand in water and stirred it around, there would be more sand at the bottom of that glass than there would at the top. So that's not homogeneous. You can tell the difference between the part. So that's actually called heterogeneous. Hetero means different, remember? So we're going to talk about the different parts of a solution now. The solute is the substance that's being dissolved, and for our generic example, that's going to be salt. The salt in the salt water is the solute, and then the solvent is the substance that's doing the dissolving, and that's the water in our example. Water we call the universal solvent because it dissolves so many things on our planet. The vast majority of things on our planet are water soluble. Now, the one thing that's not is oil. You know that oil and water don't mix. Oil is not soluble in water. So everything that's oil based, like talcum powder and things like that, anything that has an oil base to it does not dissolve in water. It's why you are 70% water. Because when you digest food and take in vitamins and minerals, you want to be able to absorb them, and you absorb them because you can dissolve them in your 70% water body. So that works really well. A lot of vitamins and minerals are water soluble. Some of them are oil soluble, however. And those are the ones. Now, it's actually kind of cool for us because if we take vitamins and minerals that are oil soluble, we can actually store them in our fat cells for when we need them, and that's really cool. But things like vitamin C and all of the B complex ones, those are water soluble. Now, that's great because when we take it, we can do something with it immediately. However, it gets rinsed out of our body very regularly, so we have to keep taking it. Vitamin C pills you can take every day and still be okay because it's always being flushed out of your system. Types of solutions. So we can have a solid dissolved in a liquid, like we just talked about with salt and water. We could have liquid dissolved in a liquid. We could have a gas dissolved in a liquid. We could have a gas dissolved in a gas, or a liquid dissolved in a liquid. There's a lot of different possibilities out there, and we need to kind of look at them all. So, for example, we can put dissolved gases in liquids. For example, oxygen is dissolved in seawater and in river water. So is carbon dioxide. Carbon dioxide is dissolved in soda, and we do that on purpose because it makes our soda fizzy. We also breathe a homogeneous mixture. The air that we breathe has some oxygen in it and some carbon dioxide in it and a lot of nitrogen in it, and it's this huge mixture, and we can't see where, oh, there's a bunch of oxygen over there. You can't see it. It's homogeneous. But it is a huge mixture, so we can also dissolve a liquid into another liquid. Now, it's hard sometimes to determine which one is the solute and the solvent, but usually the solvent is the one that we have the most of. and it's supposed to be dissolving the other one, even though they just mix together. Vinegar is a common mixture that you're familiar with. And it can be solids, a solid in a solid, and granted, you have to do that at the liquid level. We melt down tin and copper, and then it makes bronze, and then when it hardens, of course, you've got one metal there, and it's a mixture. It's not chemically combined. And then we have something called suspensions. Now, suspensions are when the particles that you're trying to dissolve in are larger than those in the solvent, and they don't dissolve in it. They mix well together, but the mixture starts to become cloudy. For example, when you put flour into water, flour particles are really large, but flour is something we grind up, and so it ends up the chunk of flour that you see is actually much bigger than a molecule of salt. So when you stir it into water, it doesn't fully dissolve. Those particles are a lot bigger than the water surrounding them, and so it ends up being cloudy. The proteins in milk are the same way. They end up making that liquid a cloudy liquid. You can't see through milk because of all of the proteins in it. Now, if you've got something like flour and water, you can actually separate these out with a filter. And that's the cool thing about mixtures, is that because they're not chemically combined, you can usually filter them out to separate them. There's usually something you can do to that mixture to make it so that you can separate them. Interaction of a solute and a solvent. How do these things interact? Because they're not chemically combined, you can separate them. They interact. You know this when we worked with ionic compounds. When we put salt in water, suddenly we realize we can throw electricity through it and actually have a reaction. So, and that's because each of the ions is surrounded by water molecules. Now remember, those water molecules are polar, so the positive ends of water are going to be attracted to the negative ions and vice versa. And that's what helps us get that great positive-negative connection for the electricity to go through that liquid. Now, covalent compounds also become completely surrounded with water, but there's no positive-negative parts to it because they aren't ions. That's the whole molecule. When you dissolve sugar into water, it's the whole sugar molecule that's in there, and so there's no positive and negative parts, so it does not conduct the electricity. Properties change in a solution. Obviously, salt does not have the same properties, solid, that it does when you dissolve it into liquid. The solutes change the physical properties of solvents. With water, it doesn't connect to electricity very well. It does if you're a lightning bolt or a huge jolt of electricity, but you know, I can't zap you with a battery through water, but I can through salt water. The amount of the solute determines the extent of the change. If I add a little bit of salt, it's going to have this amount of effect, as opposed to a lot of salt, it's going to have that change affected even more. Some of the things that it does: it lowers the freezing point. Now remember, the freezing point is where you go from a liquid state to a solid state. If you dissolve a solute in that liquid, it will actually, it's more difficult now to create the crystals. So you're going to have to make it colder in order for it to work. Water has to be perfectly 0 degrees Celsius or 32 degrees Fahrenheit to form ice crystals, but if you stir something like salt into it, now it's got to work around all of these extra molecules, so you have to actually get it colder for it to form ice. This is why the ocean can be 32 degrees and still not a solid ice cube. Now, we actually use this for our benefit. We put salt or ash on the roads so they don't ice up as quickly. So when the road is wet and the air is 32 degrees and the ground should be iced up, if we put salt or ash over the road, then it actually has to be colder Now it has to be maybe 27, 28 degrees in order for it to form ice. So you're making the road safer because we can add a solute to our liquid. We also use this when we make ice cream. If you've ever hand-made the ice cream where you stir and you stir, or you push the button and it stirs it for you, whatever. There are two bowls in an ice cream maker, and the center bowl is where you put all of the yummy cream and the fruit and whatever, all the flavorings. But the outside bowl around the edge, you put ice in it, but you also put salt in it. You put rock salt in there because the rock salt forces the ice to freeze at a colder temperature. Because while water freezes at 32 degrees Fahrenheit, cream doesn't. You have to get the cream colder to make ice cream, to freeze it. And so when you add the rock salts to the ice, it actually makes the ice colder so that it will freeze the cream on the inside. Now, just like it lowers the freezing point, it also raises the boiling point, the point at which a liquid becomes a gas. If you add more solute to a liquid, it will mean it takes higher temperatures to boil it. Now, we use this too when you are cooking and you're about to boil noodles or something, and you've got this pot and you on the stove and it's boiling. You add salt to it or oil to it, or you're going to have something else that's going to add to the water, and it makes it so that the boiling point is higher. And we do this because pasta cooks better if it's cooked at a higher temperature, and you can't boil water higher than 212 degrees Fahrenheit or 100 degrees Celsius. You can't boil it higher than that unless you add a solute to it to raise the boiling point. Suddenly your water is actually hotter. Now, the cool thing about this is when you're driving a car. It used to be we put water in our radiators, and the water would go through all of these pipes in the engine and go by the hot part of the engine, and the water would suck the heat away from the engine so the engine wouldn't overheat. Now the problem with this is if you just put water in your radiator, then water has a 212 degree boiling point, and engines are hotter than that. So if you raise all of your water up to the boiling point, suddenly your engine is overheating, the radiator cap blows off, and you've got this big plume of steam coming out of your radiator, coming out of your engine, and you need to pull over. That's why we have antifreeze. We have all kinds of solutes that we put in this liquid, and we pour that in our radiator, and that has a boiling point that's much, much higher. So it can continue to be a liquid and flow through the pipes in your engine and keep it cool without busting that gasket.